This video is going to be discussing the mole. One of the issues that scientists face is that they're working with atoms, and atoms are so small that they can't be seen and they can't actually be manipulated or touched because of their small size. And so instead, scientists need to find a way of measuring and working with quantities of very small things that are consistent throughout all chemistry. And so with that said, the mole was introduced. And this is not the first time we've actually seen a term represent a number. Let me show you some examples that you may have already encountered, and most likely already have. Whenever someone discusses a dozen of something, it could be a dozen donuts, it could be a dozen boxes, everyone recognizes that that word dozen means 12. A baker's dozen, for those of you who like to buy baked goods, is that it's 12 of an item plus one more, a total of 13, a baker's dozen. For a pair, whenever we talk about pair, a pair of shoes, a pair of birds, anything, we know we're talking about two. And for some of you who've worked with paper before, you may have heard of a ream of paper. It's actually a measurement, and an official ream of paper is that it has 500 sheets of paper. So these four examples are examples where we use a term to represent a quantity, and a very specific quantity. In chemistry, the quantity that we're going to be discussing is the mole. And the mole's quantity is 6.02 times 10 to the 23rd items. If I were to write that out, it would be 602 sextillion. So that would mean it has 21 zeros after the 602 items. Now that could be a mole of carbon atoms, but it could also be a mole of oxygen atoms. And when I'm talking about a mole of carbon atoms, I'm actually talking about this quantity of carbon atoms. That means that I have 602 sextillion carbon atoms. All right, and that actually is quite a few. In fact, it's so many that if you were to count that long, it would have to take multiple generations of your family. It will be your great-great-great-great-grandchildren that will finally finish counting. If you start counting now to this number every second of every waking moment of your day, it'll take hundreds of years to reach that number. It is a large, large number. Now, as I said, just like the dozen, where you can have a dozen donuts, you can have a dozen boxes, you can have a dozen cars, a mole is simply a quantity. So I can have 6.02 times 10 to the 23rd carbon atoms. I can also have a mole of water drops. I could have a mole of students. It makes no difference what it is that you are describing, as long as the quantity is always the same, and it will always be this number. So what we're going to be doing is you're going to have an opportunity to see a video of how big a mole is, and this will be something that you're going to connect through outside of this video. But to give you a sense of what one mole looks like, you'll notice that I have here 1 mole of aluminum, and that looks like a big wad of an aluminum ball. And so you notice that the number of aluminum atoms in here is 6.02, 23 times 10 to the 23 atoms of aluminum. And if you look at the actual quantity, that totally seems like something that you can work with in the laboratory or you can handle. Here I have a mole of copper. Here I have a mole of sugar. So you notice that the quantity that it makes up, meaning how much space it takes up, changes. For example, a mole of copper takes up less space than a mole of sugar. Well, and the reason is that a mole of copper is just one atom, where a mole of sugar is C612H22O11. And that tells you that you have 12 carbons, 22 hydrogens, and 11 oxygens. That is a total of 55 atoms all together to make one atom, one molecule of sugar. And if I then have 6.02 times 10 to the 23rd of those, obviously it's going to take up a lot more space, okay? So just as a reminder, every one of these objects, and here we have water, has 6.02 times 10 to the 23rd number of items, okay? So let's use the next step of the quantity versus the mass. So we'll use a dozen bowling balls compared to a dozen ping pong balls. So if you have a dozen bowling balls and a dozen ping pong balls, do you have more bowling balls or ping pong balls? I think everyone's going to agree a dozen means 12. If I have 12 bowling balls and a dozen ping pong balls, that's another 12 ping pong balls. It's going to be the same quantity. I have the same amount of bowling balls and ping pong balls. Now the next question is, would the mass of a dozen bowling balls be the same or different than a mass of ping pong balls? I think all of us would agree that bowling balls are a lot heavier, so the mass is going to be more for bowling balls than ping pong balls. But is the quantity more? The answer is no. Remember, I still have 12 bowling balls and I still have 12 ping pong balls. Would the volume of a dozen bowling balls be the same or different than from ping pong balls? Well, for those of you who've seen bowling balls before, they are round. They're about the size of a head, where ping pong balls are probably the size of just half of your fist. In that case, which one is going to take up more space, a dozen bowling balls or a dozen ping pong balls? And I think most people agree a dozen bowling balls takes up more space. So here's an example that even though we have the same quantity of something, 12 bowling balls and 12 ping pong balls, remember calling them a dozen bowling balls versus a dozen ping pong balls, the mass of these are not the same and the volume is not the same. This is going to become important when we're dealing with chemistry. So in chemistry, you're going to notice over here that I have 1 mole of sugar versus 1 mole of salt. And you'll notice I have the chemical formula written right below here. Can you guess which one of these is going to be sugar and which one is going to be salt? Purely based on what you see on the screen. You see a container that has a white powder where there's a lot more powder, and then you have a smaller container with the white powder that has a lot less powder. They both have the same amount of each chemical, but you notice that the volume and the mass are different. Which is which? If I assume this is A and this is B, make a guess of what you think will be sugar and which one will be salt. All right, so now we're going to apply the idea of mole to a concept that's called molar mass. As we said, that a dozen bowling balls will have a specific mass. The mass is not the same number as how many bowling balls you have. If you have each bowling ball weigh 2 pounds and you have 12 bowling balls, that means you have 24 pounds of bowling balls, okay? So they are not connected to each other. We call the mass of an entire mole of something, and remember a whole mole is 6.02 atoms, we call that a molar mass. In other words, if I pile a whole mole of carbon onto my scale, so here I have 6.02 times 10 to the 23rd atoms of carbon, how much is that going to weigh? And you'll notice that my scale says it's going to weigh 12 grams. That is called the molar mass, all right? So in that case, we know that 1 mole of carbon has a mass of 12 grams. So the next thing that we're going to be doing is we're going to learn how to convert these things. So now let's try another one. So here I have 6.02 times 10 to the 23rd atoms of N2. Now, where you can find the molar mass is actually on your periodic table. You may have noticed that on the periodic table, we have carbon with what we call an atomic mass. Now, notice how the atomic mass matched the molar mass we had just discussed about. We said that 1 mole of carbon weighs 12 grams, and that is in fact the same number. So for the next one we'll be working on is nitrogen. So let's take a look at nitrogen. Nitrogen, it tells me on the periodic table, has a mass of 14.01 grams. So returning back to our presentation, if I have 2 moles of carbon, remember, I know that from my periodic table, one mole of nitrogen equals 14 grams, 14.01 gram. Now this number 2 tells me that I have 2 moles. So in that case, I don't just have 1, I have 2. So I can times this number by 2 to get 28.02 grams. That means that 1 mole of N2 equals 28.02 grams. There's our molar mass for N2. Let's try one more. In this case, I have carbon and hydrogen. I again look at my periodic table. On the periodic table, you're going to notice that I have carbon having a mass of 12. And if I move this over just a bit, you're going to see that hydrogen has a mass of 1. So, returning back to my problem screen, let me go ahead and change that. I used my periodic table and recognized that 1 mole of carbon has a mass of 12 grams and 1 mole of hydrogen has a mass of 1.01 gram. So in this case, my chemical formula tells me I have 1 carbon, 1 mole of carbon. Now, because there's no number here, we assume that it is a 1. And this symbol here tells me I have 4 moles of hydrogen. How do I know that I have 4 moles? Is because of this lower number. So if I have 1 mole of carbon and 4 moles of hydrogen, what does that add up to? Well, I know that I have 12 grams for my 1 mole of carbon, and I have 1 mole of hydrogen, each weighing 1.01 grams. And since I have 4 of them, that adds up to being 16.04 grams of CH4. So for every 1 mole of CH4 that I have 16.04 grams of CH4. We're going to wrap it up with that.